homework for part B. So number 1 says the process transfer function of a liquid level, the third tank of 3 tanks in a series in response to changes. The input flow can be described by K divided by tau times S plus 1 to the third power. We're going to draw a block diagram from this process under the feedback control with a proportional only controller with a gain Kc, and derive a closed loop transfer function relating to the level of the third tank to the set point. So let's first draw our block diagram. So our block diagram is we were given K is over tau S plus 1 is a third, right? And then this is controlled by our Kc, our proportional controller. And we are given some height set point for our third tank. So height set point, and this is going to have some error to it, right? So the height might not actually be the height set point, and so that's going to be the error. This will go to our height, but in between it, this height set point in that, we're going to have something that measures the actual height of the device, right? So this is what it's going to be here. So right now we have a height set point. It'll be measured what height it is, has that error, tells you what it is. Then we have our Kc, then that's our proportional controller, and that will be giving us our height. So what we want to do is we want to have a equation for our height. So our equation for our height is H is equal to our K times Kc times our error over, and then we have our tau S plus 1 to the third. And we know what our error is. Our error is going to be our height set point minus our height. So we can plug that back in. So we have H is equal to K Kc times HSP minus H over tau S plus 1 to the third, right? And so then we can change these terms. So our Kc, and so this is going to be Gc, and this is going to be a term Gp. So we're going to change that. So H is going to be equal to Gp times Gc times Hs, the height set point, minus our height. And now we're going to solve for our height. So one side is going to be our height. So we're going to multiply out our Gp and our Gc. Gc, height set point minus Gc. Okay, and then we're going to move the function, the variable that has the h over to the other side with the h. So h is equal to plus Gp plus Gc. H is equal to Gp Gc and the height set point, right? And now we can pull out our h term because it's in both the terms on the left. So we have h is equal to 1 plus Gp Gc is equal to Gp Gc at set point, right? So then we can divide and have just our height. So we have h is equal to Gp Gc at set point divided by 1 plus Gp Gc. Right? So now we can plug back in our functions, so our variables that we had for Gc and Gp. So it's going to be G height is going to equal So the first term is going to be k, kc, times the height set point. Oh, and before we do this, our height set point is going to be a over s, which is just going to be a over s is going to be the magnitude of the step. So the length of that, or the magnitude of the step. So k over kc, and then divided by tau s plus 1 to the third over 1 plus kkc over tau s plus 1 to the third. So we're going to multiply this bottom term right here out to that 1 right here. So I'm going to come over here to do this. So h is equal to kkc over tau s plus 1 to the third over ts plus 1, so tau s plus 1 to the third plus kkc over tau s plus 1 to the third. And so these terms cancel out here. So I'm going to rewrite it on the next page. So we get h is equal to kkc over our tau s plus 1 to the third plus kkc yeah. So this is the answer for part 1. So this needs to be multiplied by our AS. So over here as well, this needs to be multiplied by AS, which is the magnitude of the step. So that needs to be on there. So this is the end of homework. This is the end of part 1. So part 2 says that using the criterion, determine the maximum value of Kc that yields a stable closed loop of behavior. Okay, so to have a stable loop, we need to have this. We have this polynomial under here, right? So this polynomial, we need to find the roots of this, right, to find the stability. So the root, so we can factor out this polynomial, right? So it's tau to the third plus s to the third plus 3 tau squared s squared plus 3 tau s plus 1 plus kkc. And I'm going to make this a little smaller. So this is going under our function. So this is going to be our height, right? And this is kkc over a. And then this is going to be all multiplied by s, right? So we can use this method. So it's tau to the third, and then 3 tau squared, and then it is 3 tau, and then it is 1 plus k tau. So to find the fourth term in this, we can cross multiply. So I'm going to cross multiply this term and these two terms here. So the first one we're going to get is going to be 3 tau squared times 3 tau. And then it's going to be minus tau to the third times 1 plus kc divided by our term here, our biggest term on the bottom left. That's 3 tau. And so then we can cancel out some things. So this is going to be 3t minus tau plus 1 plus kkc over 3. So our fourth term here, so we know the terms over here are going to be 0, but we want to know this term right here. So we're going to divide it by our biggest variable, and so that's going to give us 1 plus kkc, right? And so to get the stability of this, we need everything on our left side to be positive. So right now we have everything looks positive, right? The tau to the third, the 3 tau squared, and the 1 plus kkc. But over here on this function, there's a negative here, right? And we know that k is going to be positive, assuming that. So we know that if it gets to a bigger number, that this is going to become negative. So we are going to find out when kc, what is the maximum value kc will be before this term becomes negative, right? And before we have instability. So 3t minus tau times kkc. So when this is greater than 0, so we want to find that value that it turns negative, right? So you have 3 tau plus kkc over 3, right? So our taus cancel out on both sides. We can multiply this 3 over, so we'll have 9, and then we'll have 1 plus kkc. And then we can subtract that 1 over, so we'll have 8 kkc. And then we'll solve for our kc, right? So 8 divided by kc is kc. So 8 divided by k is going to be less than kc. So at this moment is going to be the greatest value that kc can be before this term becomes negative and we'll have instability. So that is the end of question 2. So then we'll get into the Python. I'm going to be doing the part 3 of this. So part 3 is confirm the results for B2 via the simulation for k is equal to 12, tau is 1.2, and in response to the step change increase at the set point of 0.12. So I imported this from our GitHub. So the first thing we want to do is put in our initials. So our k is going to equal 12. And then our tau is going to equal 1.2. And then we know our step change is going to equal 0.2. Let's check. Yeah, 0.12, right? We know that our GP is equal to k divided by tau times s plus 1 to the third. And then we know our GC is equal to 2 divided by 3. And then we have our big function, so our GC1 is going to be equal to our GP, well, GC times GP, divided by 1 plus our GC times our GP. So after this, we want to have our function, and we want to solve for our time and then our height deviation, right? So this is we're going to use the function sim, and the function we're going to use is our GC1, and then we're going to use lambda, and we're going to use the timescale of t, and we are going to have is our step change, which is our a, and then we're going to have the number of amount of steps, which is 1,000, and then the size of our steps, which we're going to use as 0.1. So then let's make our subplots. So fig will make underscore subplots, and then fig dot add underscore scatter, and then our x is going to equal our timescale, our y is going to equal our height deviation, and the mode is going to equal lines. And it means here and here. Okay. So let's see what graph it makes us. So right here that we see there's consistent peaks and valleys. It's not getting higher or lower, so this means that it's stable. So we have a stable Kc. So we're at the maximum stable Kc. So let's increase it to see what instability looks like for this, right? So let's do 1 point. And then let's look at our graph. So you can see that it's like very low here. We're having low peaks and valleys, and it's getting increased up here. So it's getting increased up here. So we can see that this is unstable. But if you want to see like over a lot of period of time, right? Because this is 10 seconds, 90 seconds. Let's do an increase of our step, our size of our steps. So over a really increased period of time, you can see how it is really getting unstable. So this does prove what we were given of the maximum value of Kc before it becomes unstable. So that's the end of homework 4 Part B. Thank you.